Hey guys, and welcome back to Mr. Cole's class today. All right, so specifically, we are getting into a little bit of a new section here. So let's go and start talking about magnetism, and especially magnetism and electricity. So let's start going through these notes. Magnetism, electricity. Magnetism, a force of attraction and repulsion between unlike poles. And so, it's kind of fun when we start talking about magnets. A magnet is a material that attracts certain materials like iron, nickel, and cobalt. And usually what we have in mind are these magnets, kind of like what we see on the screen, the traditional horseshoe magnet. Or here, this is a bar magnet, and this is actually kind of neat. This is actually, this last one, the end, that's actually what's known as a cow magnet. And obvious enough, the name describes it. A cow magnet is actually made to give to a cow to let it swallow so it can prevent what's known as hardware disease. Sometimes cows have habits of eating metals or things like that. So you feed the cow this magnet and it swallows it. And as it goes through the cow, it picks up little tidbits of metal and it, anyway, comes out as a pile on the ground eventually. So let's kind of get into specifically what it is to actually be a magnet or to magnetize something. Now, normally the first thing we would do a lab before we even looked at these notes about describing what a magnet is and this attraction and this repulsion. But in this case, we're going to go ahead and look at something. So a lodestone is just a name for a natural magnet. In other words, a magnet that you can literally dig out of the ground. It has a north pole and a south-seeking pole. Some metals, soft iron, can become magnetized and make what's called a temporary magnet. So let's talk about what it is to actually magnetize something. So if you would, imagine every single particle of iron. So let's look at this bar of iron, Fe, ferrum. Let's look at this bar of iron, and every little particle of iron that's in here has a north and a south pole. But if you take a look, every single particle is oriented in a different direction. So in order to magnetize something, all you've done in order to magnetize it is actually align every single north and south pole and orient them, every particle, in the same direction. So this is what happens. This is why iron is able to move a little bit easier than other materials. So that's why if you ever hear of something referred to as a temporary magnet, it's because guess what this magnetized material wants to do over time? Well, something made out of a soft metal will want to return to its previously unmagnetized state, as you see over here. So in the notes, you'll see I wrote, steel is harder to magnetize, but it holds its magnetism. And so the ability and how many of these particles you can orient can determine the strength of the magnet itself. So permanent magnets are made of mixtures of like iron, aluminum, nickel, and cobalt. So let's kind of go through and keep taking a look at a few things here. My screen got messed up. One of the things you might be familiar with is what's known as a neodymium magnet. And it's one of the strongest magnets in the world, especially for its size. So I pulled this off of a place that actually sells the magnets. And what's cool, this is a rare earth metal. And what's cool about these magnets is this is the reason why we first were able to take speakers from being huge speakers and start making little headphones and things like that. It was because we were able to get these very strong but small magnets. And so that's kind of an interesting little thing. So these neodymium magnets, and you can usually order those, and it's kind of funny. They used to be hard to come by. Now we kind of find them everywhere and used in a ton of applications. Some magnets are made from ceramics or powdered ceramics. So if you've got a little refrigerator magnet, if you've ever looked at it, and I challenge you for a little home science experiment right now, take two of these magnets, and believe it or not, they're still essentially the same north-south, made up of these little particles all oriented in the same direction. And what they've done is those are ground up pieces of iron. That's why if you look, the backing of these magnets is usually kind of a black color, and that's because it's made of iron embedded in this material and it's magnetized. If you've got one around the house, try and do something, because we always talk about this attraction and repulsion between magnets. And one of the cool things you'll notice is try and take two magnets and like lay them on each other, like the backs of them against each other. You should be able to find the grain of the magnets, because you'll feel them literally stick to each other as you try and drag them across each other, because you're dragging them essentially across the grain, or opposite grains. So if you laid another refrigerator magnet so that it was oriented in an opposite, the particles in it were lined up in an opposite direction of the other one, you would feel the two magnets basically kind of stick to each other. So it's kind of a little neat thing to do with those magnets. All right, and so I've got something here. Magnets are the strongest at the poles because there's no force counteracting it. Go back to that last page that we were at a little while ago. If you look all through the magnet, and this is the coolest thing, what happens if you were to break a magnet in half? Well, you get two magnets. But one of the most common questions is, where is a magnet the strongest at? And again, this is where in lab, what I would have you do usually is go grab a bar magnet, north, south, and then come back and actually lay a sheet of paper on it, and then we would sprinkle iron all over it. And one of the coolest things we would see is we would literally see, and I usually have you as students sketch this stuff out, you would literally see a pattern that looks like this, and you would see a very well-defined pattern on the ends. But around the middle, you would see a little bit of a weaker pattern established around the magnet in terms of the middle of the magnet. What you're seeing is the magnetic field around that magnet. The reason why the field is so strong at the ends, if you look throughout the middle of the magnet, you've got these north and south poles here directly aligned to each other. But on the ends, there's nothing in opposition to the ends of this magnet, so it allows this field to be at its strongest on the ends of the magnet. So moving back to the other page, our north, our south, our refrigerator magnets. Magnets are found, and here's some uses of magnets as soon as my screen stops misbehaving so terribly. Hopefully, wow, it is really going crazy. So one of the things you'll notice is if you've ever messed around the back of a speaker. I remember as a small child, actually, my brother having some speakers, and I accidentally poked a screwdriver while I was playing with the magnet part of it. I shoved a screwdriver through the cone accidentally. So anyway, to this date, I still don't think he knows what actually happened there. So I probably shouldn't confess it now via, oh well, what's the chances him watching this? So anyway, they're found in microwaves, clocks, motors, speakers, maglev trains. This is actually a train in China. It actually literally levitates off the rails. And what this does is this basically brings your frictional force down close to zero, or very close to zero. And what's kind of cool about that, I think this train is actually somewhere in the neighborhood of 327 miles per hour for a train. That could be kilometers per hour. That would probably make, yes. No. Hey, good. Bonus question. Go look up how fast can a maglev train travel. So that'd be pretty interesting to look at. But these are all uses of magnets. So the magnetic field itself, and you know in physics we use a symbol for everything. So the capital letter B is how we denote a magnetic field. And we measure magnetic fields in Tesla. You can also measure them in what's known as Gauss, although I typically don't use that too much in discussion anymore. So a 1 Tesla, by the way, a 1 Tesla magnet is a pretty strong magnet, is what it boils down to. A very strong magnet would be considered a 1 Tesla magnet. So as we move on, a region in which magnetic forces are present, measured in Tesla. A field creates a force on charged objects. So if you were in physics in particular, we would look at this. This Q represents charge. And what's kind of cool is magnetic fields can exert forces. So the V is velocity. And we're not going to work any of these. This is just an overview. and B is the magnetic field itself. So say, for example, you had a magnetic field. Let's say you had a north pole of a magnet oriented, and here is that magnetic field. B, leaving the magnet. Well, often, like physics, one of our very common problems then would be to send a charged particle, say, for example, an electron. And we've talked before about the charge of an electron is 1.6 times 10 to the negative 19 coulombs. We would send that electron through there, and then we could actually do what's known as the right-hand rule on this particle, and we could actually tell, which, interestingly enough, we're not doing that in this video, but this particle would actually get pushed, literally, and it's incredibly hard to do that via a one-dimensional video pad. But essentially, this particle would actually be pushed out of the screen. Literally, this particle would be pushed out of the screen at you, is what would happen as it traveled through this field. So one of the coolest things I used to do previously, like old television sets, I used to love going up to the old-fashioned television sets. And if you're wondering, Mr. Cole, it's been too long, we don't know what an old-fashioned television set is. Yes, you do. It was the television sets that were like weighed 60 pounds, and if you looked at them from the side, they were like 12 inches thick. You may even have an old computer monitor somewhere in your school that's like that. Coolest thing in the world, although I do not guarantee it won't permanently screw it up, lay a magnet on the screen, and actually you will then see beautiful little colored patterns appear all over the screen at that point, because the magnet, this was known as a cathode ray tube, and it actually literally was like having an electron gun in the back. That is a terrible little E, but it would shoot electrons at the screen and make the screen glow and form the colors that are on there. And so magnets would cause these electrons to fly off path, and they would go absolutely insane because of it. And sometimes the TV would actually stick that way for a day or two. So anyway, if you've got a massive old television, go for it. Might give you an opportunity to buy a new flat screen. All right, so I'm going to do something for a second. There's a little PhET simulation of a bar magnet before we go any further. And I want you to look at something. What happens when you get a compass near a bar magnet? Well, take a look. The south end of the compass always points where? Towards the north end of the bar magnet. And again, this is something in a lab we usually end up playing with. It's a little PhET like this, and we watch how this thing behaves as it goes out. Well, what's also interesting, look at what happens as we approach the south end of the magnet. Now the north end of the compass actually now points towards the south end of the magnet. Now, what's cool is usually we think about compasses not for playing with magnets on screens. Now, let's do something. This thing will actually show the magnetic field. So if you remember a little while ago, we were talking about magnetic fields, and you can kind of see how these magnetic fields work around the magnet and these patterns that they create. And what's cool, like you can sprinkle iron over a magnet and you would actually see the same pattern that we're looking at here. The other thing that's also kind of interesting in terms of playing with the iron then is to get other magnets near this one and look at the effects, because you can see the fields kind of go together. Let's do something. I want to pull up the Earth here. Now this is interesting. If you're really looking at this picture of Earth, you'd think, wow, this must be like a Southern Hemisphere class I'm teaching. Well, something that's crazy is, look at this. It's saying that what we call north, in other words, the Earth's North Pole, is actually the South Pole of the Earth. Well, that is true. The north end of the magnet that we use in a compass, and all a compass is a tiny, all a compass is a tiny little magnet that's allowing itself to line up. In other words, it's no different than this bar magnet. Essentially, the Earth itself has a bar magnet directly through the center of the Earth. And so when we look at this, and somebody's going to be literally trying to think about this concept of a bar magnet in the center of the Earth, but what happens when you're using a compass for like guiding, what's happening is the north end of your compass is actually pointing towards the South Pole of the Earth, which is actually, and what's funny is everybody thinks that the North Pole is like somewhere like geographically, yes, Geographically speaking, that is the North Pole of the Earth up there. But what we want to look at is not geographic North Pole. We actually want to look at magnetic north. And if you notice, it's actually a little bit lower up here in Canada. And so that leads to a problem when you're navigating. So one of the things, and I used to actually teach a class where we would actually go out and basically hike and that kind of stuff. The geographic North Pole of the Earth and the Earth's magnetic North Pole are actually about 2,000 kilometers apart. And actually, it probably a little different now because this actually changes. Now, what's interesting is at this time, like where I'm teaching this, I actually live in a part of Alabama that is literally a compass where I live in eastern Alabama. When it points north, it literally points the same as geographic north. But now there's a problem with this. Compasses have this little problem called magnetic declination. The compass is always going to point towards magnetic north. Now, this is a little extreme. Now, old maps used to have a little thing at the bottom of the map, and you'd see a little thing that looked kind of like this at the bottom of the map, and it might say 9 degrees. And you would see magnetic north on the bottom of a map. And the thing is, everybody uses GPSs now, so they've forgotten how to actually navigate. But you would look at the bottom of the map that you were going to use. And as you look at the bottom of the map, you would actually see this little declination, this 9 degrees. And what it told you is this. Go back over here. Say we were out towards California. And you actually you wanted to literally head from point A to point B. And you grabbed your compass and you just followed your compass due north on your compass. Hopefully you can see a problem. You would end up nowhere near where you were after. So what you would have to do is use the bottom of your map, identify your declination, and then you would be able to actually adjust for it with your compass so you could actually head north. So that's an interesting little thing, and that's actually for this video. This is far enough is where we're going to go with this declination, primarily because my battery is dying. But anyway, take care, and I'll shoot a follow-up video here in a second. So, bye.